Hey guys, this is our first video about differential equations, which differential equations and slope fields are the last two topics that we're going to have to learn to be prepared for the AP exam. And they're very closely related, which is why we do them together. So a differential equation is an equation where the variable is a derivative. And what I mean is, like, here's an equation, y prime equals 2x, which we could also write like dy dx equals 2x. And this is a thing, this is an equation where the question here is, what is y? What is f of x? What is the function whose derivative is 2x? And you might be like, I know the answer. The function whose derivative is 2x is the same question as what's the antiderivative of 2x? And you'd be like, well, I can tell you one. How about this? How about y equals x squared? This is like a possibility. Y equals x squared. Because then if y is x squared, then dy dx is 2x. And so that checks out. That's like what I was hoping for, right? I was given this, the derivative of some function is 2x. What is the function? That's the question. What is the function? And I came up with one. I was like, all right, x squared. This one was relatively straightforward because we kind of already know from doing integrals and antiderivatives over the past month or whatever that the function whose derivative is 2x is the same thing as what is the antiderivative of 2x. Antiderivative of 2x is x squared. But we really know that another possible number one was this. Another possible answer is maybe like y equals x squared plus 1 or something. The derivative of this was also 2x. So these things, these differential equations, don't always just have one answer. Sometimes there's a literal infinity of answers like there is here. So really what we could say is in general, if dy dx equals 2x, then y is x squared plus c, where c is just some arbitrary constant. It could be 1, like it was up in this example, or it could be 10 or negative 50 billion or anything. So this is like a kind of, you might say, like a general solution to this differential equation. This is, again, this differential equation asks, if dy dx is 2x, what is y? And we have decided that y could be x squared, it could be x squared plus 1. Or really, when we add the 1, we realize I could really add any constant here. So really, in general, if the derivative of some function is 2x, then that function must be x squared plus some arbitrary constant. So again, I might refer to this y equals x squared plus c as a general solution to the differential equation. These up here, where like here we had c was technically 0 and here c was 1. This is like a particular solution to the equation. This is called the general solution. The particular solutions will always have constants, will always have numbers in them, and the general solution will always have a plus c because it's like one where we don't know. So just to summarize, dy dx is a differential equation with a family of solutions. We call them a family, where it's like x squared plus 1, x squared plus 2, x squared plus 3. That's what when I say a family, I mean all of those different solutions. In general, we would just say plus c right here. A particular solution could be x squared plus 1. I'm going to rewrite that. I should say y equals x squared plus 1. Particular solution could be y equals x squared plus 1, because remember, the question here is what is y, so the answer should be y equals something. We could say that y equals x squared plus 1 is a solution differential equation with the initial condition of, and this is the part that's a little bit, it's going to be hard to understand this when I write it the first time, but you'll see what I mean when we do a couple examples. With initial condition of y of 0 equals 1. So we're going to talk about these initial conditions. They're called initial value problems, but basically what this is saying is that when I plug a 0 in for x, I get that y equals 1. This is function notation. You could write f of 0 equals 1 if you wanted to also. It doesn't really matter whether we use y. We tend in our math to say that y equals f of x. These things are very interchangeable, and at least in high school math. So if we say y of 0, that means f of 0. It means that when x is 0, the function value is 1. And you can see up here that's true. When x is 0, if x is 0, then y is 1. Because when x is 0, y equals 1. And so, right, solutions, differential equations are numbers. We're kind of used to, in our general algebraic equations, you solve for x or something, and that's the answer. But in this case, the answer is a function, y equals x squared plus 1. So how can we solve them? So there's a method which is known as separation of variables, which is what we're going to use in AP Calculus, at least in AP Calculus AB. We use only this one method. This is the only way you're going to have to do it. So if you're ever given a differential equation and asked to solve it, you must do it this way. And if you don't do it this way, you're not doing it right. So separation of variables, only specific differential equations can be solved this way. There are other ways to solve other ones. And it turns out there's only a very specific couple of types of differential equations can even be solved at all. And the ones that are really interesting, that describe real things in great detail, are unsolvable using any kind of math that anyone's aware of. So we're going to focus on just this one very specific class, but that's good for you because it means that you only have to know how to do this one thing. Anytime anybody says solve differential equation, you can know that you're supposed to use separation of variables. So here's what we do. This is called separation of variables. So unsurprisingly, we're going to separate the variables. And when I say that, I mean we're going to get all the y's on one side and the dy's. Get all the y's and dy's on one side of the equation, all the x's and dx's on the other side. So for example, if I start off with dy dx equals 2x. Again, we already know the solution to this is x squared, but we're going to use it as an example because it's kind of straightforward. The dy, there's no y's in this besides the dy, so I'm going to leave that here on the left side. And then I multiply both sides by dx. And these kind of cancel out. And so I'm left with dy equals 2x dx. So what I just did there was I separated the variables. That one wasn't terribly difficult. There was only one thing to do, which was to multiply both sides by dx. But it was, that is what I mean when I say separate variables. If I look at this now, I have all the y's and dy's on the left and all the x's and dx's on the right. It doesn't matter which variables on which side as long as they're isolated, they're separated. So this is kind of like your first step is to separate the variables. I know you guys like steps. And then the next step is going to be to take integrals on both sides. So I'm going to do an integral here. I'm going to do an integral here. And the integral of dy, it's like the integral of 1 dy. The integral of just dy is just y. And the antiderivative of 2x, we know, is x squared plus c. X squared plus some constant. And now we're done. Remember, the question here, dy dx is 2x. The implied question here is, what does y equal? We already knew that it equaled x squared plus c. Let me do one more thing here real quick, because I didn't do this. The integral of 1 dy is really y plus c. Right? It doesn't, like, this is an indefinite integral, so you have to add a constant. And then this side was x squared plus c. And you're like, well, so do the C's cancel out? It kind of looks like they might, but they don't. Because really these C's, they're not the same C. The C, remember when we looked up here, when we did this, we were like C could be 0 or C could be 1 or C could be any number. So really this is like an arbitrary constant. We call it C1. We call this one C2 or something. And then to get Y by itself, because the question here is what is Y equal? You'd say Y equals X squared plus C2 minus C1. But really this whole thing, this is just arbitrary constant minus an arbitrary constant is just another arbitrary constant. C3, maybe? But really, we just call it C. Basically, we get into this question of, is C minus C equal to 0? And the answer is no. C minus C equals C, because the C's could be anything. And it doesn't matter what they are. So really, this C1 over here and a C2 over here kind of always end up being just this C here. And people almost never write this first one. That's why I'm so used to doing that, I didn't even do it the first time. I'm gonna write this again with the 1 a little clearer so we can see where the antiderivative came from. It's the integral of 1 dy. It's like 1. The dy is like a 1 dy. So the integral of 1 is the variable, which in this case is y. So that's separation of variables. We'll do this other one because it's like a specifically initial value problem, and then I'll take a little break. So find the particular solution, which means there's not going to be a C, an arbitrary constant in the end, to this differential equation y prime minus 8x equals 0. And they give you an initial value, which is important. This tells me that when x equals 2, y equals 16. So I might want to write this y prime as dy dx when I start, because we're going to be multiplying by the differentials. I'm going to move, I'm going to add 8x to both sides. So I get dy dx equals 8x. Because again, I'm trying to separate variables. So I definitely don't want the 8x on the same side as the dy dx, because that has a y in it. I move that over. Just like in the last problem, I'm going to multiply both sides by dx to get the x's all on one side. I end up with dy equals 8x dx. And like we saw before, this is really 1 dy here. So I'm going to do integrals of both sides again. And the integral of 1 dy is just y plus c, but I'm not going to worry about that because I'm going to put a c on the other side, like we saw last time. The antiderivative of 8x is 8x squared over 2, which is really 4x squared. And now I'm going to add the c on this side, because it doesn't matter, again, whether I have a c here and a c here or just one on one side, because the c's are arbitrary. So this is what we would call a general solution. General solution. But we really want this particular solution where when x is 2, y is 16. So I'm going to plug that in here. So 16 for y, and then x is 2. I'm going to do my order of operations correctly. 2 squared is 4, and 4 times 4 is 16. So I get 16 equals 16 plus c, which means c is 0. And now the last step is to rewrite this with the value of c I just discovered. Plus 0 is just 4x squared. So this is my particular solution. No c left in it. I eliminated it by using my initial condition. And this is how separation of variables works. They can get the expressions, the initial differential equation, get a little more complicated. But if it can't be separated, they won't ask you to solve it. Not on the Calc AB test. It's just not done. The only thing you're expected to know how to do is separation of variables. So we'll come back, we'll do a couple more of these and talk a little about slope fields, and that'll be that.